Hello viewers, in this session we will continue with the properties of complex numbers, geometric, arithmetic, etc. Okay. So, firstly last time we saw the modulus of a complex number, okay, and we also said what the argument of a complex number is. So, we will see a couple of more properties of the modulus. Okay. So, last time recall we proved the triangle inequality for the modulus of complex number. So, it said that the modulus of z 1 plus z 2 is less than or equal to modulus of z 1 plus the modulus of z 2. Okay. And it was an exercise to show that equality occurs only when z 1 and z 2 lie on the same line passing through the origin, okay, and on the same side of the origin. Okay. So, that's your triangle inequality. Okay. So, it can be generalized. Okay. So, it can be applied to n numbers. So, maybe well, using induction one can show that, using the principle of mathematical induction one can show that the modulus of sum of n complex numbers like that is less than or equal to the sum of the moduli. One can prove this using mathematical induction. Okay. So, exercise prove this by using mathematical induction. Okay. And it is convenient to record one other form of triangle inequality. Okay. It is as follows. So, the modulus of the modulus of z 1, okay, plus z 2, okay, okay, or let me say modulus of z 1 minus z 2. Okay. So, let us estimate this, okay, plus z 2, okay, which is equal to the modulus of z 1. Okay. So, I am adding and subtracting z 2. By the triangle inequality, if I treat this as one number, complex number, and this as the second complex number, by the triangle inequality this is less than or equal to the modulus of z 1 minus z 2 plus the modulus of z 2. Okay. So, now using this and this on two sides of this inequality, what we get is that the modulus of z 1 minus the modulus of z 2 is less than or equal to the modulus of z 1 minus z 2. Okay. And this is symmetric in z 1 and z 2. By that I mean the modulus of z 1. Okay. So, the modulus of z 1 minus z 2, okay, is likewise greater than or equal to, we can show the modulus of z 2 minus the modulus of z 1. Okay. By doing this using z 2 instead of z 1. Okay. I mean doing the same procedure here, you will get modulus of z 2 minus z 1, but that is the same as the modulus of z 1 minus z 2. Okay. And then so you get this other part. Okay. And so, in conclusion, the modulus of z 1 minus z 2 is greater than or equal to, since it is greater than or equal to this and this, okay, it is greater than or equal to the absolute value of the modulus of z 1 minus the modulus of z 2. Okay. So, this form of a triangle inequality is also useful sometimes. Okay. And I have proved it here for records. Okay. And next what we are going to do is we are going to give a geometric interpretation using or a geometric locus using the modulus. Okay. So, we know the geometric interpretation of modulus as the distance of the complex number z from the origin. Okay. So, the modulus of z, for example, here is z, let us say. Okay. So, the modulus of z represents the length of this line segment from 0 to z. Okay, that's your modulus. Okay. And since a circle is the set of all points which are at a distance which are at a constant distance from a fixed point. Okay. So, we can say that a circle in complex plane has an equation the modulus of z minus a is equal to r. Okay. So, the modulus of z minus a measures the distance of z from a. Okay. So, a is the fixed point, okay, a is the center, okay, and modulus of z minus a is the distance of a varying point z from the fixed point a. Okay. And r is, we are I mean this equation is telling you that this distance has to be constant r. Okay. So, r is the radius of the circle. I will first talk about the geometric. Okay. So, consider the geometric interpretation of multiplication of complex number multiplication. Okay. And then I will come back to the straight line business. Okay. So, if you have z 1 equals r times r 1 times cosine theta 1 plus I sin theta 1 and z 2 equals r 2 cosine theta 2 plus I sin theta 2 for some r 1 theta 1 and r 2 theta 2. Okay. Let us assume for the time being z 1 not equal to 0, z 2 not equal to 0. So, that they have a polar representation like that. Okay. Then z 1 times z 2 we can work out is r 1 r 2 okay, times when you multiply this expression with this expression you get cosine theta 1 plus theta 2 plus I sin theta 1 plus theta 2. Okay. So, this complex number z 1 times z 2 has modulus r 1 times r 2 and an argument for z 1 times z 2 is theta 1 plus theta 2, okay, where theta 1 is an argument of z 1 and theta 2 is an argument of z 2. Okay. So, the interpretation one can give is, let us take a simplistic picture. So, suppose this is z 1 okay, and then it opens with an angle theta 1 from the positive x axis, okay, and then suppose this is z 2 and it opens with an angle theta 2 from the positive x axis. Okay. Then your z 1 times z 2 is going to have a modulus. Okay. So, the length of this line segment is going to be modulus of z 1 times modulus of z 2 like we see here. So, it is going to have r 1 times r 2 as its modulus, okay, and then it is going to open with the x axis, okay, positive x axis with an angle theta 1 plus theta 2. Okay. So, that is your geometric interpretation of multiplication. Okay. And note that argument of n argument of z 1 times z 2 okay, is equal to an argument of z 1 plus an argument of Z2. Okay. So, if you take a particular argument of Z2, Z1, any argument of Z1 for that matter, and any argument of Z2, recall there are many possible values of theta 1 and theta 2 that you can take, because cosine and sine are 2 pi periodic. Okay. So, any choice of theta 1 and theta 2 will give you this equation. Okay. This multiplication rule dictates that equation, and so you get this equality. So, the n argument for Z 1 times Z 2 is argument of Z 1 plus the argument of Z 2, or plus n argument of Z 2. Next, what I want to do is I want to look further into multiplication. Okay. So, we saw that Z 1 times Z 2 is equal to R 1 R 2 cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2, okay, where Z 1 is R 1 cosine theta 1 and Z 2 R 1 cosine theta 1 plus I sine theta 1, and Z 2 is R 2 cosine theta 2 plus I sine theta 2. Okay. So, this we saw. So, as a consequence, if you consider Z equals R cosine theta plus I sine theta, I will drop the subscripts. Okay. Then Z squared is equal to R squared, okay, cosine theta plus theta. So, that gives me 2 theta plus I sine 2 theta. Okay. So, likewise, we can show using mathematical induction. Okay. So, using the principle of mathematical induction, I will just say MI. Okay. We can show Z power n is a positive integer, is equal to R power n cosine n theta plus I sine n theta. The base case is clear. Okay. Base case n equals 1. So, then Z power 1 is equal to R power 1 cosine 1 times theta, which is theta, plus I times sine 1 times theta, which is sine theta. Okay. So, this is true. Now, suppose Z power k for some positive integer k greater than 1 is equal to R power k cosine k theta plus I sine k theta. Okay. Then Z power k plus 1 will be Z power k times Z. Okay. And then by using this supposition, which is the induction hypothesis, I can say this is equal to R power k cosine k theta plus I sine k theta times Z. Z is once again R times cosine theta plus I sine theta. Okay. So, this is equal to R power k plus 1, I will club this R power k and R, okay, and then multiply cosine k theta plus I sine k theta with cosine theta plus I sine theta. So, you get cosine k theta cosine theta, okay. I times I will give you a minus, and then sine k theta sine theta, that is the real part, plus the imaginary part is I times cosine k theta sine theta plus sine k theta cosine theta. Okay. So, that gives you R power k plus 1 times, of course, this is cosine k plus 1 theta, cosine k theta plus theta, which is cosine k plus 1 theta plus I times, this is sine k theta plus theta, which is sine k plus 1 theta, sine k plus 1 times theta. Okay. So, indeed you get Z power k plus 1 is R power k plus 1 cosine k plus 1 theta plus I sine k plus 1 theta. Okay. So, by the principle of mathematical induction, so by the principle of mathematical induction, Z power n is R power n cosine n theta plus I sine n theta. Okay. So, So, this statement is true for positive integers, okay, for any positive integer n. It is also true for negative integers and 0. Okay, well, 0 by convention, z power 0 by convention is 1, okay, and so that will tally with r power 0 cosine 0 plus I sin 0. Okay. So, this is by convention, and so this is true for n equals 0. Okay. So, the statement that z power n is r power n cosine n theta plus I sin n theta, okay, is true for n equals 0. By the way, of course, we need that this is z is not 0, otherwise we do not have the argument or an argument for z defined. Okay. So, we need all this is true only in the case of z not equal to 0. Okay. Likewise, we do not define 0 power 0, okay, it is undefined, and z power minus 1 is indeed, well, it is 1 by z, which is 1 by r times cosine theta plus I sin theta, okay, and by multiplying and dividing by cosine theta minus I sin theta, we get r in the denominator. Okay. So, cosine theta plus I sin theta times cosine theta minus I sin theta gives you cosine squared plus sine squared. So, that is times 1. Okay. So, this can be written as 1 by r, which is r power minus 1 times cosine minus theta plus I sin minus theta. So, it is true that z power minus 1 likewise is r power minus 1 times cosine minus 1 theta plus I sin minus 1 times theta. Okay. So, now either by using induction, okay, or by using what was already proved, we can show that z power minus n positive integer, okay, z power minus n is r power minus n times cosine minus n theta plus I sin minus n theta. Okay. So, you can do this directly by using the fact that already this is true for positive integers. Okay. So, this is true for positive integers. Okay. So, z power minus n is z power n power minus 1. Okay. And then by using this loss of exponents, which will work, okay, and then this is equal to 1 by z power n, etcetera. Okay. So, this is this gives you r power minus n. I mean, if you do what we have done already here, okay, you have to use the De Morse formula first, okay, or sorry, you have to use the fact that z power n is r power n cosine n theta plus I sin n theta. Okay. This is what we have done already, n is a positive integer, okay, and then write this as 1 by r power n, which is r power minus n, and then multiply and divide by cosine n theta minus I sin n theta to get cosine minus n theta plus I times sin minus n theta. The denominator will give you cosine squared n theta plus I sin plus sin squared n theta, which will give you 1. Okay. So, z power minus n will also be this. Okay. So, it is true that z power n is r power n cosine n theta plus I sin n theta for all integers n, okay, for any integer n. Okay. And this is referred to as a De Morse formula. Okay. So, all right. So, De Morse formula can be put to use at least in the following way. Here is an example. Okay. So, find the fourth roots of z equals minus 3. Okay. So, consider this example z equals 3 cosine pi plus I sin pi. Okay. So, we can write if we take the argument of z to be pi, okay, we can write z like that 3 times cosine pi plus I sin pi. Okay. So, De Moivre's formula suggests that if you want if you say w equals z power 1 by 4, you want the fourth root, okay, w power 4 is equal to z. Okay. So, w power 4 you imagine w in the place of z here. Okay. So, if w is taken to be 3 power 1 by 4 times cosine pi by 4 plus I sin pi by 4, okay, then definitely then by using De Moivre's formula, we get w power 4 is 3 power 1 by 4 power 4, which is 3 times cosine pi plus I sin pi, okay, which is your minus 3, okay, which is your z. So, definitely this value of w will work, but is this all? Okay. Well, the answer is we are missing out on other values of other possible values of w by considering one particular argument for z. Okay. We can do better by considering a general argument for z. Okay. So, if we consider z to be 3 times cosine 2 k pi plus I times sin 2 k pi plus pi, which it is because sine and cosine are 2 pi periodic, okay. K belongs to integers. Okay. Then by doing the same, what we can say is that w equals 3 power 1 by 4 times cosine 2 k pi plus pi, now divided by 4 plus I times sin 2 k pi plus pi divided by 4 is such that w power 4 now gives you z. Okay. It gives you that z. Okay. And so, then now the question is how many different values does w give? Notice that now this 2 k pi has been divided by 4. Okay. So, you get for example, when k is 1, okay, you get 2 pi by 4 pi by 2 plus pi by 4. Okay. So, for k equals 0, 1, 2 and 3, we notice that we get different values of w. Okay. So, let me be slower. Okay. So, maybe I will say w is 3 now 3 power 1 by 4 times cosine k pi by 4 plus pi by 4, sorry, k pi by 2 plus pi by 4 plus I sin k pi by 2 plus pi by 4, where k belongs to integers. Okay. Now, notice that if values of k equals 0 and k equals let us say 4, okay, give the same w. That is because when you substitute 4 in there, you get 4 pi by 2, which is 2 pi, and then I mean k pi by 2 is equal to 4 pi by 2, which is 2 pi, and cosine and sine are 2 pi periodic. So, cosine k pi by 2 plus pi by 4 will be cosine 2 pi plus pi by 4, which will once again give you cosine pi by 4. Okay. So, k equals 0 gives you this part gives you 0 plus pi by 4, okay, and then for k equals 4 you get cosine 2 pi plus pi by 4, etc., and these are equal. Okay. Likewise, sine, okay, gives you same values when k equals 0 and k equals 4. Okay. So, you get the same W as a result. Okay. So, for k equals 0, 1, 2 and 3, okay, we get all the distinct values, because k equals 1 and k equals 5, k equals 2 and k equals 6, etc., they will all give you the same values for W. Okay. So, pairwise. For k equals 0, 1, 2, 3, we get all the possible values, all the different possible values of W. Okay. So, when we work it out, well, when we substitute and see what the values are, we get W equals let us see 3 power 1 by 4 times plus or minus 1 by root 2 plus or minus I by root 2. Okay. So, all the possible combinations 1 by root 2 minus I by root 2, 1 by root 2 plus I by root 2, etc. Okay. So, minus 1 by root 2 plus I by root 2 and minus 1 by root 2 minus I by root 2. Okay. So, these are different possible values of W, okay, which give you W power 4 is equal to Z minus 3. Okay. So, those are the fourth roots of minus 3. Okay. So, De Moivre's formula can be used to solve this example, okay, or to find nth roots of a certain complex number in general. Okay. So, next we are going to need the notion of the complex plane with the point at infinity. Okay. So, so far we have this complex plane, okay, and then what we can do is we can add one point at infinity. Okay. And this is to discuss, this will be useful, this gadget will be useful to discuss continuity of certain functions as these functions tend to 0, tend to infinity. Okay. So, and in the discussion for Mobius transformations, for example. Okay. So, but we are going to give this C union infinity, this set C union infinity a concrete picture. Okay. So, what we are going to do is we will consider the complex plane as contained in R 3. Okay. So, consider right here. Okay. So, consider C as contained in R 3, okay, triples of real numbers, okay, in the form x plus I y, okay, or which is now in the plane form, it is x comma y. Okay. It is contained in R 3 in the form x comma y comma 0. Okay. This is a point in the x y plane in R 3. Okay. So, here is the plane x y plane in R 3, and we have this z axis coming out. Okay. So, this is the x axis, the y axis. Okay. So, what you can do is now you consider the unit sphere. Okay. So, okay. So, consider the unit sphere S equals set of all x, y, z such that x squared plus y squared plus z squared is equal to 1. Okay. So, this set intersects the x y plane in the unit circle. Okay. So, when z equals 0, okay, this equation is just x squared plus y squared is equal to 1. Okay. So, that is the unit circle in the complex plane. Okay. And then complex plane contained in R 3. Okay. Now, what you can do is you can take any point in the complex plane here, which is now sitting in R 3, okay, and join it to the north pole of this sphere by a straight line. Okay. And that straight line hits the unit sphere S at some point. Okay. And you notice that if you take any complex number on the x y plane, okay, corresponding to it, there is a unique point on this sphere, okay, by joining, okay, which is obtained by joining the number on the complex plane to this point at this north pole, which is the point 0, 0, 1. Okay. So, we can find out what that point of intersection of that line is. Okay. So, to do that, you consider t times 0, 0, 1, okay, plus 1 minus t times x comma y comma 0. Okay. So, this is the point z in the complex plane, okay, and then this is the point which is the north pole, okay, the north pole. Okay. And so, this t times 0, 0, 1 plus 1 minus t times x y 0, when t is allowed to be any real number, okay, gives you a straight line connecting 0, 0, 1 and x y 0. Okay. We know how to construct equations of lines in R 3. Okay. So, t times a point plus 1 minus t times another point will give you a line passing through these 2 points. Okay. So, so this is a point in R 3, let us call that capital Z. Okay. So, capital Z equals this, okay, is a straight line, okay, in R 3 connecting 0, 0, 1 to a complex number to the complex number x y 0. Okay. Now, the complex numbers are on the x y plane. Okay. So, now the point of intersection of this line we can calculate with the sphere, okay, is obtained by, well, S is set of all points, I already wrote it here. So, S is the set of all points such that x squared plus y squared plus z squared is equal to 1. Let us look at the x, y, z coordinates of this capital Z. Capital Z, let me rewrite that as it is t plus 1 minus t times x. Okay. So, that will give me x, sorry, t times 0. So, that gives me 1 minus t times x, and then t times 0 times 1 plus 1 minus t times y, that gives me 1 minus t times y likewise, okay, and t times 1 plus 1 minus t times zero gives me t. Okay. So, now that is your point z, and when we put it on the unit sphere, we get 1 minus t squared x squared plus 1 minus t squared y squared plus t squared is equal to 1. Okay. But x squared plus y squared is the modulus of a complex number z. Okay. So, if we call this number z belongs to C, we already called this z belongs to C. Okay. So, this is 1 minus t squared modulus of z squared plus t squared is equal to 1. Okay. Now, let us solve for t. Okay. So, we get 1 minus t squared is equal to 1 minus t whole squared modulus of z squared. Okay. So, t from here we can solve for t. Well, notice that t does not equal 1, because when t is equal to 1, when you substitute t equals 1 in here, okay, you get 0 0 1. Okay. So, there is no there is no complex number, okay, which intersects this sphere in this point 0 0 1 itself. Okay. After all, you are connecting the complex number to this point 0 0 1. Okay. So, that will not intersect the sphere in 0 0 1 itself. Okay. So, t will not be 1, okay, because since this corresponds to the point 0 0 1. Okay. So, you can divide by 1 minus t squared, for example, okay, and then if we solve this for t, okay, we can solve this for t. Well, let us do it. Okay. So, 1 minus t squared is modulus of z squared plus t squared modulus of z squared minus 2 t modulus of z squared. Okay. So, this gives you t squared times modulus of z squared plus 1 plus minus 2 t times modulus of z squared plus modulus of z squared minus 1 is equal to 0. Okay. And so, excuse me. So, t then is okay, by using the quadratic formula, okay, what you can get is t is modulus of z squared minus 1 by modulus of z squared plus 1. So, substituting t in this point capital Z, we get the following. Capital Z is equal to 2 x by modulus of z squared plus 1, comma 2 y by modulus of z squared plus 1, comma modulus of z squared minus 1 by modulus of z squared plus 1. Okay. And if you want to write this completely in terms of the complex number z, okay, we will remove the appearance of x. Okay. So, this is z plus z bar by modulus of z squared plus 1. Okay. So, that represents the conjugate, recall, okay. Z bar represents the conjugate of z, and then minus I times z minus z bar by modulus of z squared plus 1, okay. And then this is modulus of z squared minus 1 by modulus of z squared plus 1. Okay. So, that is your point of intersection of the line joining the north pole and a point z on the complex plane, okay, with the unit sphere. Okay. So, that is the point z. Okay. And then okay. So, if we wish to find, okay, if we are given a point, okay, the opposite is if we are given a point capital Z, okay, on the sphere on S, okay, then we can find the point Z on the complex plane, okay, then Z on C can be found. Recall, what we are doing is we are drawing a straight line connecting 0 0 1, okay, and the point capital Z, okay, and that gives you and when you project it onto the complex plane, it gives you a point of intersection with the complex plane, okay, and we can calculate that. So, that can be found, we get Z equals x 1 plus I x 2 by 1 minus x 3, where capital Z is assumed to be x 1, x 2, x 3. Okay. Once again, x 3 is okay, is not 1. Okay, x 3 is not 1, because x 3 equals 1 will correspond to the north pole. So, I should say that if we are given a point z on S not equal to 0 0 1, okay, then we can find z on the complex plane. Okay. So, by this kind of association, okay, corresponding to each point on the sphere, okay, there is a point on the complex plane, and corresponding to each point on the complex plane there is a point on the sphere. Okay. So, there is a one-to-one correspondence between points on the sphere and the complex plane. We actually have the equations for them. Okay. And then these points, the one-to-one correspondence is given by geometrically drawing a straight line passing through the north pole and the point on the complex plane. Okay. Or in the other direction by joining the north pole and any other point on the sphere, okay, on the sphere, which will be projected onto the complex plane to get the complex number. Okay. So, in this way there is a one-to-one correspondence, but notice here that we have accounted for all the points on the sphere except the north pole. Okay. And let us look at the picture once again. Okay. And as you move farther away in the complex plane, okay, you are moving higher up on this sphere. The point of intersection of the line joining that farther away point on the complex plane and the north pole will be higher up here. Okay. So, and so you keep approaching the north pole, but you never reach the north pole by these lines which are intersecting the sphere. Okay. So, in that sense when you move far away you are getting closer to the north pole. In that sense the north pole represents the point at infinity. Okay. So, you think of the point at infinity as the north pole. Okay. And then so, that is the correspondence of points in C union infinity with the points in S. Points in C go to points in S which are anything but the north pole, okay, by that straight line connecting north pole and the complex number, okay, and the point infinity itself goes to the north pole. Okay. So, that is the correspondence. And this sphere is often called the Riemann sphere. Okay. When we put some distance also on this. Okay. So, we can put a distance on okay, can give a distance function on C union infinity. Okay. We can find the distance between any two numbers z and z prime in C union infinity. Okay. So, this is define this as the distance between okay. So, actually it is a split definition. Okay. So, define this to be the distance between the corresponding point z and z prime on the sphere, okay, in R 3, okay, distance in R 3, when z and z prime not equal to infinity. Okay. We are defining distance function for C union infinity. Okay. So, forget infinity for the time being. If you take any two complex numbers, okay, the new distance on the okay, in C union infinity is defined to be the distance between the corresponding points z and z prime in R 3. Okay. And then if you have infinity, okay, in picture, okay, so then you can also define distance. What you do is you define this to be 2 by 1 plus modulus of z squared, okay, power half, if z prime is equal to infinity. Okay. If z prime is infinity, then this is the thing. Okay. And if z is infinity, of course, you have 2 by 1 plus z prime modulus of z prime squared power half. is raised to power half. Okay. So, so let me rewrite this as the distance between z and z prime is x 1. Okay. So, in terms of x 1, x 2, x 3 representing z and x 1 prime, x 2 prime, x 3 prime representing z 1 z prime, we have x 1 minus x 1 prime squared plus x 2 minus x 2 prime squared. Of course, that is the distance in R 3 plus x 3 minus x 3 prime squared power half. Okay. And then this is equal to 2 by 1 plus mod z squared power half, okay, if z prime is equal to infinity, if z or z prime not equal to infinity. Okay. So, that way we can measure the distance between any two points. The only new point is infinity, but actually we measure distances using the distance in R 3. Okay. And okay, so, this correspondence, okay, this structure on C union infinity, okay, is often called the Riemann sphere structure, okay, and then this correspondence along with this distance, okay, is called stereographic projection. Okay. So, using the stereographic projection, okay, we have this point at infinity, okay, being added to this this complex plane. Okay. And then in C union infinity we have arithmetic as well. Okay. So, a plus infinity is equal to infinity for a belongs to C, okay, and then a times infinity is infinity, a belongs to C, a by, okay, a not equal to 0. Okay. We do not define 0 times infinity, okay. And then 1 by infinity is equal to 0, okay. And then or a by infinity is equal to 0, a belongs to C, and then 1 by 0 or a by 0, a belongs to C is infinity. Okay. So, we have this additional arithmetic, okay. And then okay. So, this is a discussion about the Riemann sphere. So, we have added a point at infinity in addition to the complex numbers, okay. And then there is a distance measuring gadget as well. So, we will put this to use when we study Mobius transformations.